Hello, everyone. Welcome to another episode of Q&A about history of science and technology for kids and others. So I see a whole bunch of questions saved up here. This is one that's okay. One from Atori. Can you talk about lambda calculus? I'll try. This would be easier if I was allowing myself to show you things on the computer and so on. But let me try and give some background and try and explain this. So lambda calculus is an idea from 1935, actually, that was one of the different possible models for what computation might consist of. So these days, we use computers all the time. We have some idea of what it means to do a computation. One can think of a computation as being something where you define certain rules, and then those rules get automatically applied many, many times. That's what the computation is. Back in the early part of the 20th century, there was an attempt to particularly take all the things that sort of happen in mathematics and say what's in common between all these different things one does in mathematics, whether one's doing geometry or whether one's doing algebra or whether one's doing arithmetic. What is the sort of common infrastructure, the common raw material from which one can build up all those different areas of mathematics? And people had a bunch of different schemes for what that might consist of. The fundamental thing people imagine doing is just write down sort of a symbolic expression, make something that has, things like an f of x or f of g of x of whatever. These are things where we're not necessarily saying what f and g are. They're just kind of a structure. Now, for example, when we have an expression, an algebraic expression, like something like 2x plus y squared, we can think of that, and this is what we do in Morphin language, as a times of 2 and x. There's a plus outside the whole thing, and then there's a power of y and 2, whatever I said. And we can think of it as a symbolic expression, plus of times of x of 2, comma, power of y and 2, or whatever. Well, the big idea was that sort of all these different things that come up in math, whether you're representing arithmetic, algebra, geometry, group theory, other kinds of things, could all be represented in this kind of symbolic expression way. It was kind of an idea that sort of came into existence, I would say, in the late 1800s, 1880s, 1890s, and so on. And then there was a chap called David Hilbert who pushed this idea. Whitehead and Russell kind of pushed this idea. They kind of they thought of it as being sort of derive everything from logic, although implicitly they were also using the symbolic expression idea. Now, I have to say that I kind of cottoned on to the symbolic expression idea in the end of the 1970s when I was designing the sort of forerunner of what's now Wolfram language. And it's all based on everything that I've done in sort of our computational language and so on, is all based on the symbolic expression idea, which really dates originally from the early part of the 20th century. And it had some uses in the intervening years, but what we've been able to build, the kind of tower of capability that we've been able to build in the Wolfram language, is certainly something I hadn't imagined one could build such a tall tower, but it's all based on this idea of symbolic expressions. Okay, how does this relate to lambda calculus? Well, you have these symbolic expressions, and they might represent some algebraic formula, they might represent some piece of geometry, whatever else. What are you going to do with them? You have to have some kind of way in which they kind of do operations. So, for example, if you had a piece of that symbolic expression that represented 2 plus 2, you want it to be the case that that gets evaluated to 4. You have to have something which is kind of animating this symbolic expression, making it do things. And so you have these rules that define what to do. If you see a piece of symbolic expression that looks like this, what are you going to do with it? The first, well, you could think of logic as being a little bit like that. If you say P and P, you can transfer you can transform that to just P. just like if you say, you said P plus P, where plus is a arithmetic addition, then that's equal to 2 times P and so on. Well, kind of the question was, what's the sort of general way to represent those transformations? There were several different ideas. First one was due to a chap called Moses Schoenfinkel in 1920, was the idea of combinators. They're very, very abstract. They're very hard to understand. I wrote a book about them a few years ago. They are, even 100 years later, they're very hard to understand. And people didn't understand them then, and it sort of didn't really engage and get a lot of people to pay attention. Then there was a chap called Emil Post, who started talking about essentially string rewriting systems, where it's kind of a bit like a text editor, where you say, if you have a string that goes, AAA, BBB, you should replace that with BA or something. That was another idea. That was from 1921. Then there was another idea from 1931, which was called general recursive functions, which were Kurt Gödel used that idea in proving Gödel's theorem. And then in 1935, Alonzo Church, a mathematician at Princeton, had the idea of what he called lambda calculus. And how to explain lambda calculus? Lambda calculus is a way of describing kind of transformations for symbolic expressions. And the idea is more or less this. So let's say you say I have a function f, and you're going to say f of x is x squared. What does that really mean? In Wolfram language, the way that that would be specified is f of x blank, where blank is an underscore character, colon equals x squared. What does that mean? It means there is a pattern of the form f of any expression, that's the blank. We're going to name it x. F of any expression should be transformed to that expression squared. So that's kind of a way of thinking about what a function is. It's a thing where you have the symbolic expression of the form f of any expression, and that is then transformed in the way that I just specified. Okay, so that's one view of sort of what functions are, is they are things that transform symbolic expressions to other symbolic expressions. Okay, so the lambda calculus idea is if you've got something like f of x is x squared, how do you make a kind of pure anonymous function that is what f itself is, in a sense? You've said what f of x is, that it's x squared, but can you just say what is f itself without talking about the x? And the idea is that f itself is lambda of, let's call it z squared. What does that mean? When we're saying lambda of z, one says we're going to expect something that's going to be fed into that z slot, and we're going to take that thing and square it. And so the idea of a lambda expression, a pure function, sometimes called an anonymous function because it doesn't have a name, as it's not f, it's what f is, what you can think of as being the pure f function. It's this thing that says lambda of z, which means basically I'm expecting something, something that's going to be fed in, lambda of z squared. So that means I'm going to eat any expression, and I'm going to take that expression and square it. So that's a lambda function. And the idea is that you can write sort of something, that lambda function is then reduced. So if you say lambda of z squared, and then you say apply that to x plus 1, let's say, it'll bind the x plus 1 to the z, sort of eat the x plus 1, and turn the result to x plus 1 squared. So there's sort of a reduction rule that's it's usually called beta reduction, that essentially takes the pure lambda expression and you're feeding it things, you're applying that lambda expression as a pure function to things, and then it is being reduced to the result of feeding that thing into its bound variable and then turning it into the body of lambda expression. This is hard to explain. I probably shouldn't have attempted this without actually typing things on a computer. But to give you sort of the flavor of it, a lambda expression is a pure function, a disembodied function that has no name. It is just a thing that says, I am expecting to eat an expression, and this is what I will do with that expression if I am fed it. And the point is that you can write programs and things as big collections of lambda functions. And then the running of the program is just the lambda function doing the transformations that lambda functions do. And it gets very kind of funky because you can have sort of very pure lambda expressions that aren't really applied to anything. They're just doing reductions like beta reduction by being applied to other lambda expressions. And actually, I was just studying this recently, the kind of ruleology of lambda expressions, and trying to understand if you have just pure lambda expressions, you can have a situation where you basically the lambda expression will sort of eat another lambda expression and produce another lambda expression. It will keep going. It'll never stop. Or even it will even grow and it will produce more. It's eating lambda expressions. It's producing lambda expressions. It's just producing this bigger and bigger structure. So those are sort of obscure pure computation ideas. But the main idea is it's this way of sort of abstracting the function out of the sort of the pure function. If f of x is x squared, what is f itself? You can think of it as a pure function. Things like that are very useful. I mean, in Wolfram language, we call it the function function. It is a function whose name is function. It gets written with an ampersand and things. It has a nice short form, but it is the function function. And you might say, well, why do I want a function function? Well, then it turns out to be very, very useful. I would say that in people learning Wolfram language and so on, at first people will say, I don't need anything that abstract. I don't need that pure function thing. It's way too abstract. And they don't use it at first. And then at some point when they've sort of by hand done the things for which pure functions are really useful, eventually you can show them a pure function and it'll be like, aha, okay, now I get it. Now I can automate, simplify a lot of things I've done in the past. A typical example is you want to apply some operation to the same operation to lots of different things. So let's say you have a bunch of images and you're going to invert the colors, find the edges, et cetera, et cetera, et cetera. What you want to do is you might say, well, I'll write a function that does all those things, and then you'd map that function over all those images. But you might say, I don't want to bother to write out that function and write f of x blank colon equals, and then that definition of edge detection, whatever. I just want to put something in that stands for that function. And that's what you can do. You can just say something like, edge detect of hash sign and then ampersand. That thing is a pure function which can now serve the role of a function that can be applied to all those images. So that's kind of the idea, and that's how it ends up being useful. Let's see. Very different question here. From Memes. Asks, any thoughts on numerology? Actually, let me just see if there are more comments on them. Okay. Okay. Well, what is numerology? Numerology tends to be, oh, I notice that this thing in the world, like the mass of the muon divided by the mass of the electron, which is roughly 206, that really that ratio is actually very close to the square root of pi divided by 7 to the power 3, who knows what, something that's just pure numbers. So numerology is sort of the correspondence between things that are purely made of numbers and things that you see kind of in the real world. That's the most common use of that term. Occasionally, there's kind of within mathematics numerology. People notice that there is some kind of coincidence that, oh, this series of numbers that appear in this mathematical problem are the same series of numbers that appear in that mathematical problem. There have been a number of cases most notably in studying large finite groups and things, where that kind of numerology has paid off. We're noticing in mathematics that this sequence is the same as that other one, that then a connection was found between the source of those sequences. Numerology has a much less good history in natural science, and even worse history probably in kind of more human oriented areas. It's kind of, you know, there are many examples of people trying this. It's really basically, as I'm thinking about it, I don't think it's ever worked. You know, one thing that's often the target of this is a thing called the fine structure constant, which is a characterization of the strength of electromagnetic forces. It happens to be dimensionless. It's just a number. It's roughly 1 over 137. And people say, well, we should be able to just derive this from something lower level. If we have a fundamental theory of physics, for example, we should just be able to derive the fine structure constant. And one day I would hope that our theory of physics will be able to do that. It's worth realizing, just sort of a footnote to that story, is that the fine structure constant as a strength of electromagnetic forces really depends on the observer observing those forces. The value of 1 over 137 is only really correct for an observer that's operating in a sense at very low energy, an observer who, in the uncertainty principle, kind of relates energy to length scales, an observer who is kind of measuring electromagnetic forces on a very large length scale. As you probe them on shorter length scales, the effective value of the fine structure constant changes. So it's a little bit tricky to just sort of say, oh, well, we should have the fine structure constant just fall out of the theory. It's the thing that falls out of the theory has to be something whose value depends on the observer who's observing the thing. But in any case, there's sort of an effort to it's not been a good story of people trying to find, you know, oh, it's really square root of pi times this and that and the other. Now, you know, it's worth trying to understand the sort of theory of numerology. I will tell you something, that if you type into Wolfram Alpha some just random number, 1.7284643 or whatever, it will have a pod that comes out that lists possible closed forms. It will tell you what ratios of pi's and things like this are close to the number you typed in. Now, it has a bit of a trade-off, because you could get something that's exactly the number you've typed in, but it's a sum of 8 powers of pi divided by lots of powers of e and so on. It could be a really complicated formula. It's sort of completely unsurprising that there is a really complicated formula that represents, you know, the 6 digits you typed in of that number. After all, if we really wanted a formula for the number 1.17 or something, the formula will be 1 plus 1 over 10 plus 7 over 100. And that's a nice, in terms of whole numbers, formula. It's just not telling one very much, because that really is just the number you put in. Now, if the number that I put in was 3.14159, then it might be telling me something to say that's just pi. I could say that number is 3 plus 1 over 10 plus 4 over 100 plus whatever, but that's a kind of a long description of the number. The thing that's interesting is if there's a short description of the number in terms of things like pi or whatever else. In a sense, the mission of numerology, I suppose, is to say, is there a small formula for all the digits that you know of that number? It's kind of a thing where it's like asking, you know, you can think of that powers of pi or whatever else as like a program for making the number. And so essentially numerology is this question of, is there a short program that makes my number? I can clearly have a program that's about the same length as the number itself that just writes down the number, but is there a short program that makes the number? Now, even that's a tricky thing to say, because the question of what kinds of operations can be in that program. For example, I talked about pi and so on. People have heard of pi, but how about if I talk about, I don't know, the next level of obscurity would be the Euler-Mascheroni constant, or another level would be, you know, the Madelung sum of some lattice. These are all kinds of things that can be thought of as mathematical constants, but they have an increasing level of obscurity to them. And so then you have the trade-off of, well, you know, how many pies is one Madelung constant equivalent to? Because if I introduce obscure enough constants, then again, I'm kind of, for example, I could just invent a constant that is my personal constant, that is the number I just typed in, and then I've got a very short description, but you don't know what my personal constant is, that you have to have a whole sort of chain of knowledge of that. So in a sense, sort of the question is, if you have a certain language for describing your number, that might include pies, square roots, things like that, how small can the description of your number be? And that's a reasonable question. There are clearly, if you think about all possible numbers, most of them can't have short descriptions because those short descriptions are much fewer in number than all the possible numbers with all their digits. But this question of sort of how much is a pi versus, what's the effective sort of description length of saying I've got a pi, as opposed to I've got a Madelung constant? Interesting question. Not obvious what the answer should be. Like 15 years ago, when we were building that capability in Wolfram Alpha, what we did was this. We looked at basically all kind of easily available math papers, academic papers, and we simply say, how often do these constants appear? Pi appears all over the place. The Euler-Mascheroni constant, much less frequently. The Madelung constant, even much less frequently. And then what we said was, let's say that the sort of effective information content of saying it's pi is much smaller in proportion to how much more frequently it appears in mathematical literature. Like if I say it's pi, I probably don't have to tell you anymore. If I say it's the Smith constant, I'm going to have to define what I mean by the Smith constant. And so that was sort of a way of getting a proxy for sort of what the effective amount of information associated with saying it's constant such and such. Now, having thought about that, you're kind of in this position of saying, well, if I've got some number that I just measured in the world, how small a program can I make for that number? And is that significant and so on? And if I have that small program for the number, can I imagine a mechanism by which that number would be the value that it is? Let me give you an example within mathematics. If you look at a pair of numbers, let's say 12 and 4, okay, or 12 and 8. Okay, 12 and 8 are not relatively prime. What does that mean? It means there is a divisor of 8. 8 is 2 times 4. 12 is 4 times 3. Okay, the 4 is in common between those. So those numbers have a divisor in common. They are not relatively prime. If we were to talk about, let's say, oh gosh, let me not fail my arithmetic here. Let's talk about 10 and, what's a good example? 10 and 21, okay? 10 is 2 times 5, 21 is 7 times 3. I'm so proud of myself, I'm now beginning to know my multiplication tables. I didn't know them when I was a kid. I've gradually learned them over the course of my life. But in any case, 10 and 21 are relatively prime because they have no factors in common. Okay, so I can ask the question. Let's say I try a whole bunch of different numbers, and I ask, what's the chance that two numbers are relatively prime? And the answer, I'll get some number. I forget what the exact number is, but I go in and get more and more and more digits. And then maybe I type it into Wolfram Alpha and I say, what is this number? It's going to say it's 6 over pi squared. Well, that turns out to be a piece of numerology that works because it really is 6 over pi squared. And there is a mathematical argument for why it has to be 6 over pi squared. And so that's a case where sort of the numerology works out. And as I say, sometimes it does in math. I'll mention this question of kind of numbers and kind of how producible is that number. So let's say that I've got a number and it is producible as 6 over pi squared, for example. I can imagine that if I'm just looking at all possible numbers, I might type in 6 over pi squared and that might be the number I generate. But let's say that you've just got the number 1.73842654379, whatever. I don't think I'm very good at generating random digits, but it's just some sort of randomly generated sequence of digits. Is that number a readily producible number, or is it a number that doesn't have a short formula that I'm ever going to encounter, and it's really a number that I'm very unlikely to find? Is it a number whose chance of occurring is about proportional to 10 to the minus the number of digits that I've specified? So you might say, why would anybody care about knowing whether a number is producible in that sense? I'll give you an example. Back in the early 1990s, there was a big disaster. Intel, semiconductor company, had made the Pentium chip, was the 8586 microprocessor. Lots of fanfare, exciting, faster, better, the new technology microprocessor. Somebody noticed that a particular set of numbers, if you divided one number by the other, you got the wrong answer. The Pentium chip just gave the wrong answer for a particular division of two particular numbers. So then the question was, how much does that matter? Because if you were just picking numbers at random based on their digits, the chance of hitting the number that was one of these bug numbers was incredibly low. I mean, ridiculously low, to the point where certainly wouldn't have happened in human history with people running Pentium chips all the time. But if that number was a producible number that turned out to be really it's 6 over pi squared or something to enough digits, then much bigger deal, because one could really imagine that that number would actually show up in practice. Turns out, so far as I could ever tell, the numbers that led to the bug were not producible numbers. By the way, this term producible numbers, I just invented that 3 minutes ago or something. It's not a standard term in the literature of mathematics and so on, but I think it's a good term for this particular idea. So that's sort of an application of this, that's sort of an inverse numerology kind of question of, oh, there is no simple version of this number, so we don't have to worry as much about the fact that there is a bug in that case, because the chance that that number occurs is really, really small. Well, so that's a few comments on numerology. I'll mention one more thing. It's a thing called Benford's law. And it's one of these things where it's like, well, this is a weird numerical feature. So if you look at typical kinds of numbers that occur in practice, like, I don't know, the market caps of public companies, or the kinds of numbers that you'd see on a bank statement, and you ask the following question. You say, what's the first digit of that number? Is it $131? Is it $372? Just take the 1 or the 3 or whatever. Question is, do all leading digits of numbers occur with equal frequency? Well, the answer is that in most sort of practical numbers that show up in accounting statements or whatever else, they don't occur with equal frequency. 1 is much more probable than 2, and so on, going down to 9. It turns out, so why is that? Well, the reason is that when you do mathematical operations, in a sense, what matters, the slightly technical thing to say is the logarithms of these numbers are equally distributed, but the numbers themselves are not. And what happens, let's see how to explain this. Well, roughly, the point is that if you're picking a number and you're picking any number independent of its size, the point is that numbers that are, as you reduce it to be a number that you write out in terms of digits, when you pick the number sort of independent of size, you're more likely to land in that part of the digit representation of the number that begins with a 1 than that begins with a 9, and so on. It's kind of a standard trick for trying to detect fraud in accounting, for example. Just look at all the numbers and you just say, well, if there are really a lot of numbers that begin with a 9, that are, the amounts of payables and things like this, that's kind of fishy. And it's sort of a common heuristic for that. It works. Benford's law works for many kinds of things. It works, I think, for the powers of two. It doesn't happen to work. That's in a pure mathematics setting, not in a sort of human world setting. I don't think it works for primes, and I don't think it works for some other kinds of numbers. And it's an interesting question, which there isn't really a great answer to, of why it works in some cases in sort of pure mathematics and not in others. Anyway, a few thoughts about numerology. Let's see. Oh boy, there's some follow-on questions here. Okay, so Technic says their current favorite approximation to a constant, in this case E, is some combination of digits here. Wow, that's interesting. That's accurate. They claim to 18 septillion digits. That seems very hard to believe to me, but that's an interesting claim. I mean, this whole question about the coincidences of numbers that are sort of approximately this or that. A famous one is e to the power pi times square root of 163, I think. That number is really close to being an integer. It doesn't have to be. Could be any number, but it's very close. It's, something 0.999999 many times. Is that significant? It turns out this mathematician named Ramanujan, who was working in the early part of the 20th century, kind of noticed this and realized that it was significant, and in fact built a whole theory based on it, which, among other things, is one of the main ways that people compute the digits of pi, is using Ramanujan's theory that came from kind of noticing this kind of numerical coincidence that e to the pi squared of 163, I think that's the right one, is close to an integer. I will say that this thing about you generate numbers and then you say, what are these numbers? Where do they come from? That's something that when I do research on things, which I do all the time, I'll generate sequences of numbers, and there's a function in Wolfram language, find sequence function, which attempts to find what function describes that sequence of numbers. And quite often it's useful. Usually when it is useful, I kind of say, hey, I should have been able to figure out why these numbers are, powers of 3 minus powers of 2 or something. But it notices and I didn't, so to speak. There's an online system, OEIS, the Online Encyclopedia of Integer Sequences, built by a chap called Neil Sloan. He started in the 1960s on index cards and then a book and so on, collecting integer sequences. And it's like, what is the sequence? Oh, it's the number of ways that you can assemble sort of squares together and get patterns that are distinct when you rotate them around. Or it's the number of ways that you can assemble a tree with up to some number of nodes and so on. It's quite often the case that sort of you get you generate this from some completely different method. Then you might use find sequence function. You might look it up in OAIS, and it'll tell you, oh, by the way, that's the number of trees, as a function of the number of nodes or something. And that's a useful thing. That sort of mathematical coincidence is useful. I would say that that has been much more successful than the case of applying this to the natural world. There is sort of another case of this, which is sort of in archaeology and so on, where people say, oh, the height of the Great Pyramid divided by the size of the nose of the Sphinx is, very close to pi squared or something. That must have been significant. Usually, the truth is those things were not significant, and nobody knew that that was what was going on at the time when the thing was being built. But it is the case that there was quite a tradition of sort of hidden information, I would say, particularly in the, early printing, 1500s, 1600s, and so on, of kind of like hiding kind of messages in the weird numbers that would show up in places. There's a whole kind of tradition of that in the Kabbalah sort of Jewish tradition is a lot about sort of noticing weird numerical coincidences from the Old Testament and such like. Did the people who were writing this were they sort of hiding a secret message in the number of Hebrew characters between here and there, or is that just a coincidence? That's the question. It's always a difficult question. Once you have a thing, to know was that thing made for a purpose or not is a very difficult problem. I mean, it's, famously things like, well, famous statement from the philosopher Immanuel Kant, if you see a hexagon drawn in the sand, you can reasonably assume that it was made for a purpose by an intelligence of some kind. That goes a certain distance until you discover that there are wind-produced kind of patterns in the sand, which can be hexagons, but it's just the wind. And unless you think of the wind as an intelligence, which perhaps you should, it's certainly not an intelligence of the human kind. And even more dramatically, if you look at the North Pole of the planet Saturn, it has a giant storm that is a pretty good approximation to a hexagon. So it's like on the North Pole of Saturn, there's a hexagon right there. And so in Immanuel Kant's heuristic for was it made for a purpose, was it made by an intelligence, Saturn was made by an intelligence, which is sort of an interesting conclusion, but it talks about the difficulty of recognizing what's intelligent and what's merely the natural world doing its thing. I mean, another famous example from the beginning of the 20th century was both Marconi and, well, Tesla had noticed that if you just put a radio mast up, there wasn't a lot of radio transmission going on in the world at that time. You just put a radio mast up, like in the middle of the Atlantic, if you were on a yacht going across the Atlantic or something, you would hear all kinds of radio emissions. What were they? Tesla said there must be the Martians signaling. Marconi didn't know what they were. But what they actually are particular magnetohydrodynamic effects in the Earth's ionosphere. And they are essentially a pure piece of nature, but yet they make these sounds that you might think were of kind of intelligent origin. Now, to confuse things even further, decades later, whale songs were discovered, and whale songs sound an awful lot like these kind of emissions from the ionosphere and the emissions from the ionosphere radio. But if you play them as sound, they sound a lot like the sounds from whales and so on. So it's very confusing. We think the whales are sort of an intelligence like us. We think the ionosphere is not an intelligence like us, but can we tell what was for a purpose and what wasn't? And it's the same kind of thing when we're looking at a Stonehenge or something and we're saying, was it set up in this way because it's aligned with the equinox? Or was it set up this way just because, Druid, I don't know what Druid names would have been, Druid, Zextrix or something, I have no idea if that's a valid Druid name, but I'm sort of remembering the Asterix series of comic books that I think had some druids in it. So I'm guessing it might be something like that, although who knows. But in any case, we did this druid or whatever who decided what Stonehenge should look like. Were they thinking about astronomy and the equinox and so on, or were they just like, oh yeah, let's put it this way? And it's hard to know. And sometimes, in some of these cases, one says, yes, it's very accurately aligned so that it, so the light falls on exactly this stone at the time of the equinox or whatever. And then it's like, well, how accurately is it aligned that way? And, maybe they meant it to be for the equinox, but they didn't know their astronomy well enough. And so it isn't quite aligned. So it's always very difficult to tell. Let's see. Gosh. Reebok comments, atmospheric noise is about as random as we can get, I think. Well, actually, the thing I was just telling about the ionosphere is a little bit of giving a bit of a twist to that. I think, the wind and kind of turbulence in the atmosphere is pretty random in some sense, but there's definite regularity to it. For example, the very fact that wind has gusts is a piece of regularity that, why does wind have gusts? It's because, well, in the end, motion of fluids sometimes motion of fluids is very smooth. That's so-called laminar flow when the fluid just sort of slides past an obstacle. But when the fluid is going faster, it produces turbulence, and turbulence, you can think of it as it's making all these little eddies of air or water, if it's water that one's dealing with. And there's a sort of a general cascade that happens. When you start with a big eddy, it gets ground down to smaller and smaller and smaller eddies, and eventually the eddies kind of dissipate away. But that cascade of eddies is from the big to the small. There's kind of a somewhat accurate universal law that the energy of a certain eddy is a e to the minus 5/3 law, or k to the minus 5/3. Actually, no, that's that's the wave number. The size of the eddies varies like the minus 5/3 power of their size, and that sort of the reason for the gusting has to do with that kind of cascade of eddy sizes. So it's not completely sort of pure random, because there's some regularities from like the cascade of eddy sizes and so on. It's one of these things where when you look at it on a small enough scale, if you look at the individual molecules, you'll be like, yeah, they're pretty random. Now, of course, if you roll the clock back and you say, well, how did the molecules start off? In principle, you can do the computation to work out where the molecules will be now. It's sort of a big story that I've tried to clarify actually in recent years, that this phenomenon of computational irreducibility tells one, well, yes, in principle, you can work out where all the molecules will be, but in practice, it will take you a computation far beyond any computation you can do to figure that out. So for practical purposes, you can't know where the molecules are going to be, and you just have to say, well, they seem random because there's nothing we can say that can predict where they'll be. All right, let me see. Other kinds of questions. Here's a question that might be reasonably simple from Igor. The question is, how does IBM Watson AI stand against modern LLMs? Well, so for those who remember it, IBM Watson was a system that was put up in 2009 or 2010, and it was kind of a publicity stunt. So IBM had for many, many years worked on text retrieval, which is the problem of you've got a big piece of text online, you want to find these words from that piece of text that would be just searching for the keywords. You want to kind of say, well, where is there something in my text that's similar to this sentence that I'm typing in? And the fact that you have a lot of sentences which have the in them, just like the sentence you typed in has a the in it, that's not terribly significant. So there are a bunch of different ways to find out, well, what is a relevant match? What is a significant match? What's not a significant match? There's a technique, actually not invented at IBM, but it was sort of used there, a thing called TF-IDF, term frequency inverse document frequency, which essentially is the thing that says, if there's a really obscure word, a rhombic hexacantahedron, to pick an obscure word, that happens to be the name of the three-dimensional solid that is our company logo and so on. But it's an obscure word, or a rhombic hexacantahedron. If your document somewhere in it has the word hexacantahedron and your search query has hexacantahedron, the place where you found hexacantahedron in the document is probably really significant. If what you found in your query and what you found in the document is the word, I don't know, significant, let's say, that's less significant. If it's the word the, it's completely insignificant. So there are these methods for figuring out what's the relevant thing to pick out of a document. So IBM had worked on a bunch of these techniques, and then they kind of wanted to have, and IBM is a company with a long history of doing this, to have sort of a publicity stunt of, can we show off all this technology? I have to say, I know quite a few of the people who are involved in this whole story, so I'll give you just the external version of this. The thing that So somebody figured out, well, what's, the Jeopardy game? Again, I don't watch television, so I'd not really seen this, but it's kind of like you have a bunch of clues, and then you're kind of asked, uh, given these clues, who does this correspond to? Who's a person? What's a kind of animal that has pointy ears and bushy tail and climbs trees and this and that and the other. And it's sort of, is it I don't know what does that, but that kind of thing. So the sort of publicity stunt was to try to use text retrieval methods to sort of beat the game of Jeopardy, and which is a television TV game show. And the idea was to use web content and things like this, and essentially to do text retrieval searching based on the clues that were given in the Jeopardy game, and then surface the answers. So this was done in a kind of televised thing. The one time I watched Jeopardy on television. What was quite interesting to see was that at the bottom of the screen, they showed the runner-up kind of possible answers. And that was very revealing, because it was revealing that this really was a text retrieval play, because some of those answers had incorrect capitalization and things like this. They were really coming from the source document. It's like, here's the sentence that comes from the source document that seems to be a match. So anyway, they did that. The uh, uh, the the big thing was that the IBM machine that was very dramatically presented as this big physical machine won against the then reigning Jeopardy champion. I think in reality, part of the way that that game works is, do you lock in a win or do you try for the next clue? And that's kind of a probability estimates question. And humans are really not very good at that. Humans are always too hopeful or too pessimistic. And humans don't just kind of coolly weigh the odds and make their choices based on those. Machines are much better at that. And I think that's in the end why the machine won. It was more or less, the clues it was doing sort of similarly, but it could win on doing the probability estimates correctly. So that was the story of Watson. Came out soon after the Wolfram Alpha. Wolfram Alpha came out, and it was it never really went too far. It was I think as a piece of corporate commentary, it was sort of a publicity stunt that got people to pay attention to IBM. I mean, they spent billions of dollars advertising Watson as a way to do for your corporate data what it had done for Jeopardy, and to kind of find a needle in a haystack in sort of corporate data or medical data or something like this. Find the needle in the haystack and win big. The truth is, in many ways, and this is maybe more of a business statement, it was sort of solving the wrong problem, because most companies have their data in a pretty organized form in databases and things like that. It's all just rows of numbers and so on. And the problem ends up being, can you answer a question that is maybe stated just in plain English, answer a question relative to all that structured data? And actually, that's the technology we built in Wolfram Alpha. It was very suitable for that. It's been used many, many times for that. And it's something for which this text retrieval approach of Watson really wasn't a good idea. There's more to this story of our interactions with IBM and Watson, but I don't think I should, at least not yet, tell that on a live stream. I have to think about that. Maybe in a few years from now, maybe it's a story, it's an interesting story, and maybe it can be told. But in any case, how does that relate to a modern LLM? Well, the methodology was different. As I said, it was really about text retrieval, much more like a search engine. In fact, right after the Jeopardy win, I tried, how well could you do just with a search engine? And the answer was pretty well. The main issue with the search engine was that, yes, you could get the right answer on the first search engine result page, but knowing which of those answers from the search engine result page was the absolute winner that was more difficult. That final ranking was a bit more difficult. But okay, so for an LLM, LLMs work in a rather different way. They are taking the input text, might be a huge amount, trillion tokens, whatever it is, and they're really grinding it up. They're getting trained to replicate that text. That's their training task. But the way that they represent that text is really ground down into all these numbers inside the neural net and so on. There's no lump of text there that says, John Smith or something as a potential answer. It's the John Smith is encoded in this way that nobody really understands very well as all these little detailed numbers that are part of the neural net weights, that are part of the 100 billion neural net weights, let's say. So it will be interesting, actually, and it's an easy experiment. I'm sure somebody's tried it. I don't know the answer of how well does the modern LLM do on the original televised Jeopardy competition that Watson did. My guess is that a modern LLM will do very well at that. My guess is it will pretty much nail it, and almost effortlessly so. I might be wrong, be a good experiment to try, but that would be my guess. But the way it's doing it is very different, and even though the effect might be somewhat the same. But that's a thought on that. I mean, it's a very different. These approaches are all very different from what we're doing with Wolfram Alpha or Wolfram Language, where we're actually computing answers. In the text retrieval case, you're literally pulling out that piece of text. In the LLM case, you're pulling out that sort of statistical pattern that you learn from the pattern of a piece of text. It's not you are using essentially an algorithm to compute the answer, or you're using sort of the structured, curated data to be able to figure out the answer. That's what we're doing in Wolfram Language. It's something where Wolfram Language is a useful tool for humans. It's also become a useful tool for AIs. More and more of our customers now are AIs. Presumably, there's a human at the end of the chain who's asking the AI to do something, and then the AI is asking our technology to do something. One assumes maybe one day it'll be AIs for themselves, so to speak. But the dynamic is that the LLM is providing this kind of linguistic interface to ultimately this computation. So it's sort of a hierarchy of things, from the pure text retrieval to the kind of statistical ground up thing to the actual computation side of things. Let's see. Okay, Opie comments. Would the LLM have the same reaction time to compete and press the buzzer? That's an interesting question. That's a good sort of assessment of LLMs, because the fact is that LLMs, well, an LLM, the way it works, like ChatGPT, I think had about 400 layers in the neural net, and you're sending that data through those layers, and that takes a certain amount of time, and it has to go through all those layers for every token it produces, every piece of a word, every character, whatever that it produces. Now, can one distill the neural net so that it has fewer layers? Can one have faster hardware to run it on? Those are all things one expects to be possible. And so they'll speed up. But it's a good question. At what point you reach the Jeopardy point, so to speak, where you can win at that, given the timing information. Let's see. Let me see. Oh, there's a question here from Reebok. Is it possible that one day we'll predict the weather years in advance? I think the answer to that is no, plain and simple. I think that there are two different things. One is the sort of computational irreducibility of all that turbulence and all those kinds of things. The other thing is that in the end, you need to know precisely the way the world is set up, and precisely, what tree is growing on what hill, and what, how much plankton is there in this piece of the ocean that causes this or that thing. So to know, and even in the case of predicting the weather far in advance, how much traffic is there going to be on this road that's going to stir up the air in this or that way. So I think the sort of lack of knowledge of the future of the world kind of precludes that. Now, what level of general prediction can you make? This is kind of one of the challenges of climate work is, okay, the weather is one thing. That is the details of, what will the temperature be? Will it be raining in this place or that? Really hard to predict. Things about clouds, and when clouds form and et cetera, et cetera, et cetera. Now, if you say, well, can I say something about the weather a year from now? It's very challenging, because you're sort of, are there things that you can say in generality and approximately versus things that you can say as a matter of something like weather prediction? The transition between those things is really tricky because when you're predicting something, far in advance, you can't simulate every single blade of grass, for sure not. But even, the size of the region on the Earth that you're simulating, I don't know how big it is these days. I think it's like 10 kilometers on a side, something like that, is the grid of kind of what you can do very long-term sort of climate prediction from. It's a very coarse grid. So anything that's happening that matters about, this particular cliff that has this particular airflow and so on, it's like you're out of luck. It's just a 10-kilometer square grid section. And it's super hard to know what will happen. And there's one thing is to do a computer simulation. The other thing to do is to say, given this effect, like increasing carbon dioxide levels, increasing retention of water vapor in the atmosphere, all these kinds of things, given these effects, can we make a kind of physics understandable, human understandable argument for why this or that thing should happen? Sort of two competing methodologies. One is to kind of reason it through, kind of almost natural philosophy style, but where and the other is run the computer simulation and hope you got all the parameters right and just trust the answer. They're both fraught with difficulty. And if you can kind of make them agree and not cheat in doing that, then you have something going for you. But it's really hard. And I think my observation has been that the closer you get to people who actually do climate modeling really on the ground with computer systems, the more they say, hey, we want to just make these physics arguments, and vice versa, so to speak. It's a pretty difficult area to know, sort of to be able to say what's going to happen. But that's kind of the story of, and to know, will this happen 3 years from now? There are some large-scale atmospheric effects like El Ninos and so on, which have effects on timescales of order a few years. Similarly, things changing in ocean currents and so on. And there's some predictability on multi-year timescales, usually with the kind of physics argument type methodology, not the detailed, closer to weather forecasting type argument. Reebok is asking, then is weather a good random sequence? Well, up to a point, but there is some predictability. I mean, like if you say the temperature here is random, well, it's not really. In the course of the year, in places inland, for example, you have this essentially sinusoidal temperature as a function of time through the year. That's the overall temperature profile. Now, in detail, day to day, there may be all kinds of seemingly random fluctuations, but there's still an overarching pattern to the whole thing. Let's see, there's a question here from Brianna. How do you calculate wind speed if wind is a pressure difference? So, I mean, the easy way to calculate wind speed is with an anemometer, where, it's been the same forever and ever. It's just this little thing you see that's twirling around and has little cups that catch the wind, and it gets twirled around at a different speed depending on how fast the wind is going. That works okay if you're dealing with, like, you just stick it on a pole and you're measuring it at the surface. It's a bit trickier to measure the wind speed when you're in the air, because among other things, it's like you don't have the pole that you're attaching things to. To measure winds aloft is a trickier thing these days. I guess it's let's see how. I mean, clearly you can have a balloon if you have a balloon and you send the balloon up, the balloon is going to get blown by the wind, and you can just watch the balloon and see how fast it goes. And with modern GPS and so on, that's not difficult. I'm trying to remember how this, I mean, planes can, I'm trying to think, it's sort of an application of vectors, so to speak. The plane thinks it's going in this direction, and it has a certain thrust that it's pushing with, but the wind is blowing it in that direction, and it's sort of the vector sum that determines what the actual direction is. And I think you can deduce, in fact, yeah, I know you can deduce something about the winds at different altitudes by looking at what's happening to planes. But it's the whole question about, is the wind, for example, constant as you go up? No, it isn't at all. The wind is going in very different directions as you go up. And winds at high altitudes are routinely very fast. I mean, there'll be, if you're in a plane flying at, 36,000 feet, 40,000 feet, or even, maybe 50,000 feet or 45,000 feet or something, the winds can routinely be 200 miles an hour. Which at the surface doesn't happen that way. I mean, in general, what's happening is there's friction between the air and the surface of the Earth, and that causes the air that's close to the surface to be moving. Well, in the end, it's moving very slowly at the right down an inch from the ground or something. And as you go further up, there's kind of that sort of that effect becomes less important, and then it's just how much is the air getting blown around, so to speak. Let's see. If the Earth started rotating in reverse, asks Kuki, would that have an effect on the weather? Absolutely. I mean, at the moment when it started turning backwards, all hell would break loose. But let's assume that we just picked an Earth that was otherwise the same but was rotating the other way around. The point is that let's see if I remember which way around this goes. Cyclones in the northern hemisphere rotate in one direction, in the southern hemisphere, I'm not remember. I think cyclones go clockwise in the northern hemisphere. So that's regions of low pressure that have essentially wind circulating around them. They because of the rotation of the Earth, the rotation of the Earth leads to this sort of asymmetry between what happens in the southern hemisphere and the northern hemisphere, at least in the direction of rotation of these things. That's a result of this thing called the Coriolis force, which is a force that, let's see, it's a force that you get on a rotating object. It's roughly that if you, well, yeah, let's give an example, a practical example. If people are shooting guns, artillery, and they have a shell and they shoot it 20 miles, it goes up in its parabolic trajectory, more or less, and it comes down again. And the question is, as that happens, as the thing is going through the air, so to speak, the Earth is turning underneath it. And that effectively, as you work out all the math and so on, that ends up having an effect on then where, relative to where the Earth is, if you're fixed in knowing, if what matters is where the shell is going to fall. Is it going to fall, on that, battalion or that other one or something, or on that, where is it going to fall? That's that question of where those troops are is fixed on the surface of the Earth, but where the shell goes is during the time the shell is in the air, the Earth will have turned, and so that. You can think of that as being like a force. If you fix yourself to the coordinate system of the folks on the ground, it's as if there's a force that's pushing the shell in a certain direction. And that force, as you think about sort of the coordinates of how you define things, is in an opposite direction in the northern hemisphere and the southern hemisphere. And so, for example, when people have artillery tables back in the day when they were still to set a gun or something, you had to actually look up this table of numbers they had to have different ones for the northern hemisphere and the southern hemisphere. That effect in a less troublesome setting, perhaps, is what leads to the different circulation in the northern hemisphere and the southern hemisphere of these high pressure cyclones and so on. By the way, there's a fun story of a long time ago. There was perhaps not so directly relevant, but it's an interesting story anyway. There was a plane a fighter plane, I think, that was sort of electronically controlled fighter plane. This was in the 80s, I guess. And one feature that it had was somebody said, we've verified the code for this plane and it's correct. Of course, what does it mean for the code for a fighter plane to be correct? Because it depends what you want the fighter plane to do. And the thing that happened was the fighter plane was being tested and it flew over the equator to the southern hemisphere and it turned upside down. And now, is that correct? Is that not correct? You probably don't want the plane to fly upside down, but that was a thing. I think it had to do with correcting for the Coriolis force. I'm not sure. But it was a sort of an interesting case of, you think you've defined what it means to be correct, but unless you've thought of all the things that could happen, it's very hard to imagine what it means to be correct, so to speak. And that was a case where, rather dramatically, it was not what you would have hoped it would do, so to speak. Let's see. I see. There was a question here. Let's see. Gist is asking, what would it take to stabilize the weather, like using wind farms in reverse or controlling ground albedo so that we know it exactly? That's a good question. I mean, this is the whole area of geoengineering, which is, if we don't like the way the climate is going, how about we engineer it to be something different? And we might not like it because we feel bad about the fact that we humans are having an effect on it. We might not like it because it's causing some part of the earth to turn into a desert. We might not like it for all kinds of reasons. But let's just say we could turn the thermostat of the earth and say this is what the weather is going to be like, or this is what the climate is going to be like. It's, of course, a very complicated question. If one had that capability and it was global, where should we set the temperature to be? Do we want it to be the case that, northern Canada is a great place for growing bananas or something? Perhaps not. Perhaps we say that's too far off. Do we want it to be the case that it doesn't get quite as cold in the winter on the east coast of the US or something? Or do we want it to be the case, there are lots of different things. It's very hard to decide what you would want to do if you could just control the thermostat of the earth. It would be much easier if you could say, for, this county wants to pick this or that thing to happen. That, I think, is a more plausible, very difficult to achieve, but a more sort of socio-politically achievable kind of objective. But in any case, this question of, can we in fact control these things? The answer is almost certainly yes. There are all kinds of different approaches. To list a few of them, and sometimes you hear about these approaches, and then I'll hear about them from people, and then a few years will pass, and I'll say, well, what happened to that approach? And they'll say, well, it doesn't work because of this and that and the other thing. But a few approaches are, you put aerosols, little particles in the upper atmosphere of the Earth. It changes the albedo, the amount of sunlight that the Earth reflects, as opposed to getting absorbed on the surface. That means that the sky will be a little bit dimmer, but it means that less sunlight will reach the Earth, and so you'll cool the Earth. That's an example of an approach. Another approach is to seed the oceans with iron so that you grow more algae, and those algae will ingest carbon dioxide. It's very much like what plants do in the, plants, if you plant more trees, there are a couple of trillion trees on the Earth right now. If you planted another trillion trees, you would have some effect as well. It might be easier to seed the oceans, kind of fertilize the oceans, and get the algae in the oceans to do this. That changes carbon dioxide levels. It's not clear that The albedo change is mostly to do with retention of water vapor. So it's a slightly less direct thing, but it's presumably related. Then there are approaches, let's see, there are all kinds of approaches. What are some other ones? There are the artificial trees. That's another approach. Um, you know, controlling the wind. The fact that wind farms work insofar as they do is, and they're tricky business because wind farms are very expensive, very hard to maintain, giant pieces of equipment that, it's not clear that the economics are complicated. But insofar as it's not, people don't usually say, oh, there's a wind farm there, so it took all my wind, so to speak. There is some of that, but that's a very small effect. The amount that's removed from the circulation of the atmosphere is absolutely tiny. I mean, it's the same thing as you could say if we're using hydroelectric power and we're doing things like, for example, we're storing energy by pumping water up to a higher level and then letting it cascade down to a lower level. In a sense, that pumping act is doing something that is, well, let's see, is that, well, no, if you're harvesting energy from the tides, for example, I think that pumping thing does it as well, but to a smaller extent. If you're taking energy from the tides, you are effectively reducing the tides of the Earth, and ultimately you will affect the rotation rate of the Earth. But that effect is so absolutely infinitesimal that, all the power us humans could ever want would not have a big effect on the rotation of the Earth. I think it's that, the Earth's rotation changes a bit. That's why we have leap seconds and so on, but that's mostly due to things like earthquakes and so on. It's things beyond what us humans, the levels of energy that us humans can make use of. But I think in the question of, could you do something that has a climate effect by using sort of wind farm level technology, I kind of suspect the answer is no. I kind of suspect that it's just way too weak to have any effect there. I think that a sort of intermediate case is cloud seeding. This question of whether you can make clouds form, make clouds rain. That's been a thing that people have tried for 100 years. It's typical. It's the one of the things that is generally believed to be true is that sort of every raindrop was nucleated by something like a piece of dust or something, that when you have water vapor in a cloud, it's just going to stay as water vapor unless something kind of reminds it that it could all be clumping together. And then at the right humidity level and so on, right temperature level, it will start to clump. Typically around that nucleation site, which might be a piece of dust, might even perhaps be to do with cosmic rays and ionization in the atmosphere, things like this. It's not clear whether that's important. It's not clear whether maybe the path of lightning is determined by that as well. But the idea is let's put sort of artificial nucleation sites into a cloud and make it nucleate more quickly and then rain. And silver iodide, I guess, is one of the common substances used, I think. But the basic point is you're sort of trailing behind a plane. You've got a plane flying around and it's splurting out stuff into a cloud. And then the idea is for that to form the nucleation sites that cause the water vapor to form into droplets and then drop as rain. And people have been trying to do this for 100 years. And there have been some there have been a bunch of claimed successes, a bunch of, I think an Olympics in Beijing a few years ago, there was a claim that cloud seeding had been successful there. There's a company I know that's, one of the challenges of cloud seeding is, were you actually successful or was it going to rain anyway? It's kind of like one of these medical tests type things, if you didn't take the drug, would you have gotten better anyway? And so it's sort of a challenge to be able to figure out, what would have happened anyway, so to speak. And one's getting better at that because weather radar and one's able to sort of more accurately say these were the droplets in this cloud. And another thing you can do is just have your plane fly in a pattern And if it rains in a pattern that spells out a word, which I don't think anybody has quite achieved yet, but if it did that, if the pattern of the rain, as seen by a plane or a satellite or something, was spelling out the word hello or something, that would be a pretty convincing argument that it was really, the clouds are not going to spontaneously rain in the pattern of the word hello. So you probably really did succeed in doing cloud seeding. But that's sort of an intermediate case of local, in a sense, local climate. It's still been very challenging to make that work. Let's see. Well, Jürgen is commenting. Oh gosh, got a couple of comments in. I should go up on my way here. But Gillian is asking, can the Earth's tilt ever be affected? What changes would this cause? So the Earth is tilted at 23 degrees relative to the plane in which it orbits the sun. That's the oh my gosh, that tilt is what is that? The obliquity, I think, of the Earth. I think that's right. I mean, most of the planets rotate around in more or less the same plane as they orbit the sun. Famously, Uranus is tipped the other way and rotates backwards, but mostly it's close. The Earth is 23 degrees away. That's what leads to the seasons, is the fact that the Earth is not rotating with the amount of sunlight you get depends on different times of the year, depends on where you depends on it varies because of that tilt. There is a precession of the equinoxes. There is the Earth, its axis precesses around every 23,000 years, I think. And so this question of kind of so its tilt is, it's like a top. That's if you watch a top before it topples over, you'll see it precess. The axis of rotation will make this little circle. The axis of the Earth is doing the same thing every 23,000 years or so. But in terms of things that affect the tilt of the Earth, I'm not sure that much does. I mean, in ultimately, the moon is very tied into what's happening with the Earth, and I don't know. The moon is gradually receding from the Earth, and I don't know whether when the moon has receded far from the Earth, or in earlier times when the moon was closer to the Earth, I don't know what that will have done to the tilt of the Earth. Jürgen comments, there's a large difference between what an ideal climate would be and what changes would mean trouble for us given our current infrastructure. Yes, absolutely. I have no idea what an ideal climate would be. I think it'll be dependent. The 8 billion people on the Earth would probably all have different opinions about that. The thing that is probably the most difficult aspect of climate change is that, we have an infrastructure that in recent years has been built up to a high degree of precision, so to speak. I mean, 1,000 years ago, the climate changed. The climate changed a bunch of times. In the 1600s, it was much colder in the middle of the 1600s. Still not clear quite why, the so-called Maunder minimum that might have had something to do with the output from the sun. It's not really clear, but it was much colder then. And, and there were times when, different parts of the Earth were very fertile versus not, and so on. And, in past times, over the course of 100 years, people would just move their sheep from one place to another, and it wasn't sort of a big deal. But in modern times, we've built up a lot of, we built our condos on the beach type thing, and we built up a lot of detailed things that depend on the climate, the sea level, and so on being the way that they are right now. And that's, I think, one of the challenges, which at some level is an economic challenge, at some level is a kind of people have built up things the way they want them to be and don't want them to change type thing. But I think that's it's absolutely true that the number one issue is the effect on modern infrastructure. And even things like, questions of, how much is that piece of land worth? If you can grow crops on it, it's worth more than if it's just random, tundra that you don't seem to be able to do much with. But I think, so yes, that's the challenge is, to unravel kind of I don't know, economic effects from kind of the actual sort of physics of climate, and then I think there's a certain kind of ethical view that the Earth has been going along just fine, and we shouldn't affect it. That's more of I think, an ethical kind of statement. That it's unclear what that from an ethics point of view, that's a complicated story because it's like we got 8 billion people, and we think ethics is really a pretty human thing, and it's sort of more important in a sense in ethics as we do it normally as humans, because ethics is really only defined relative to humans. The ethics of a rock are very hard to define. What we mean by, what should we do relative to the rock? What should the rock be doing, so to speak? That's not really ethics is a human story. And so when it's a question of sort of ethics of the humans versus ethics of the inanimate earth, that's a complicated story. And that maybe is a good thing to leave for another time. Not that I know how to unravel that question, but that's that's a different kind of overlay is the is what of what's going on, and sort of how to think about the sort of the theory of whether we should or shouldn't be doing things to the earth. And if we were in a position to do, let's say we realized that it was going to be a big win to change the seasons. Let's imagine in science fiction stories, put rocket engines on the earth, and let's say we could do that, which we cannot. It's far, far away from being possible. But let's say we could, and we could change the tilt of the earth and make it be the case that we no longer had seasons. There's a whole complicated question of what that would mean, and how we should think about that ethically and otherwise. And spare parts comments, even the weather can't agree on what the weather should be. Yes, and maybe that's a good place to end for today. But thank you for asking a lot of interesting questions, get me to think about a lot of different things. And well, thanks for asking these questions and for joining me, and see you another time. Bye for now.